Yeah, so thanks a lot, Felix, for having me. So probably some people have heard, this word sort of, this idea of Goodwillie calculus bandied about a little bit. Is that a word, bandied about? And so I wanted to take, so I'm going to sort of take two parts. This is actually the topic of my thesis work, which was in pure homotopy theory. And one of the reasons I actually got interested in type theory was looking for a nice way to phrase and organize the ideas behind this subject. So in joint work with Mathieu-Hanel and Georg Biedermann and André Joyal, we've been sort of investigating the links between this subject, Goodwillie calculus, and higher topos theory, and sort of by extension, because I really like computer science, type theory. So, and I think we've started to make some real progress. So I think it's going to be interesting to sort of explain some of these ideas and sort of introduce them to the type theory community, to people who may find them a little bit more foreign. So today, what I think I want to do is kind of give you just the crash course, the basic introduction, the classical ideas where this comes from. And then I'll take the next lecture and sort of erase all of those ideas and give you a completely different picture, which reproduces the first. So let's sort of get started. Where does this idea, what is this calculus about? Where does it come from, and what does it mean? Well, it sort of starts with down in this corner here, with just some elementary homotopy theory. So I just want to do some very elementary homotopy theory. I want to think about long exact sequences. So probably everyone knows that if I have and so I'm sort of working up homotopy theoretically. So for me, sort of every map is a fibration, like a good homotopy theorist. And if I have a point and a map, so a fibration, I can look at its homotopy fiber like this. And so the fiber picks up a base point because of the assumption that, if I assume that this composite are the same, this is the same point. And then so I can take so I can take this pullback right here, and I'll see that I have a map from loop to B. Right? And then I can take this point right here, and if I take this outer pullback square, I see that I have loops on E. Yeah, and then actually loops on B has a canonical base point like this. So if I now take this outer pullback square, 1 to F, I see that I get loops on F, and I can keep playing this game. Okay, and this sequence that I get of spaces along the diagonal like this is just completely canonical. It's generated by any map as long as I have a base point. And the interesting thing is what happens when I apply pi naught, the set of connected components to this sequence, because then actually so I'm glad everyone's nodding their head. That's very good, because what's going to happen when I take pi naught of a loop space is it's going to turn into what we call pi 1. This is just the definition. So I just from starting from some map and a choice of an element in the fiber, I get this long exact sequence. So let's see, pi 1 of F, pi 1 of E, pi 1 B, mapping down to pi naught of F, mapping to pi naught of E, mapping to pi naught of B, and of course I can continue the sequence as long as I like. And these, of course, these are only sets. These will be groups, and then I'll have abelian groups further on. And moreover, the fact that this composite factors through this composite means that the composite of any of these two maps is 0. And so this is the sort of standard calculational technique in homotopy theory. Okay, so I hope, does this seem familiar to everyone? Great. So what this says, you can read this as saying that homotopy groups, and more generally sort of think of the space itself, the information of homotopy in a space is extremely compatible with limits, with finite limits. So if I have, so if I start taking limits in this sort of naive way, I generate a nice sequence. And if I know information about, say, 2 out of the 3 of these spaces, I can get information about the third. And this was called deductive arguments and methods of calculation. So, the unfortunate, so sometimes some spaces we know come presented to us naturally as fibrations. That happens, but not that often. So what happens more often is that spaces we like are presented by colimits, right? So the sort of standard way when we have a CW complex where we want to build a space inductively by spheres is you take some space, say something like the end skeleton, you map a sphere into it, and then, or maybe you map a bunch of spheres, but let's just say one for just a moment, and then you map this sphere to a point, and you take the homotopy push out of this diagram, and we call that attaching a cell to X, because I essentially look at a sphere inside of my end skeleton. Maybe I'll just do disjoint, why not? And so I pick some collection of spheres, and I fill them in, and this generates cells, okay? So we get push-out diagrams that look like this. And the spaces that we study in homotopy theory, like spheres and projective spaces and things like this, they often come to us presented like this. And this is problematic because homotopy is not compatible with this kind of construction of a space. Okay, so this is a fundamental sort of duality in homotopy theory and a fundamental source of tension about how to compute invariance when we have things presented by colimits. Okay, so let's just think for a minute. We want to compute homotopy invariance of X, some type, some space. Okay, and if we're going to imagine X sort of presented in this way, what can we do? Well, one thing we could do is we could imagine giving ourselves some functor, some function of X, let's say. So let me think of this as a functor from, well, say pointed spaces, let's say to spaces, and hopefully I won't get in too much trouble with base points at some point. If I may add a base point here if I get stuck, but anyway. So let's imagine that we had some functor, and let's think of F, applying F to some space X, as some sort of approximation, okay? So instead of computing F, we're going to give ourselves some construction. I don't know what it is yet. We're going to try and find some. And instead of computing approximate the values of X, the homotopy groups of X, let's compute the homotopy groups of F of X, okay? What conditions on F make this easy? Okay, so what could I ask about my functor F so that when I go to compute the invariance of F of X, I get some sort of easy calculation? Okay, so let's do something almost absurd, which is so we said that often spaces are presented by colimits, but that homotopy is compatible with limits. So let's just ask of F something obscenely strong, which is, let's suppose that anytime I have a push-out square, C, not to D, and I apply F to it, oops, which way did my mouse go? Let's suppose it becomes a pullback square, okay? So let's imagine giving ourselves some sort of ridiculously unlikely situation like this, where I have a functor which every time I apply it to a push-out square becomes a pullback square. So the nice thing that this does is if I had such a thing, then whenever I have a presentation by spaces by colimits, I can compute the invariance of F using this, this standard calculational technique for homotopy theory here on the right. Okay, so such a functor would have some very impressive properties, and it would help me compute invariance. Okay, that's one way to think of it, exactly. So we're gonna, yeah, for various reasons, we're gonna see the terminology is slightly different. But okay, so let me wrap this into a definition. Such an F is said to be one excessive if this holds. Okay. So if F has this bizarre transforming colimits into limits property, I'm going to say that it's one excessive. And let me say that F is linear. And, we can, the terminology is always a debate in the subject. If it's one excessive, and it preserves the terminal object. So when I apply f to the contractible type, I get a contractible type. Okay. So what happens? Well, let's just do some examples, play around with some things that happen if I give myself such a function. So, for example, in my in my example that I had before, well, let's say we just glued on one particular cell. I glue on a cell attachment to X, and then I apply F to it. And if F preserves the base point, this stays a 1 right here. And I get an F. And now this square, by my magic F, has become a pullback square. And that means that I have, well, what Homotopy would call a vibration sequence. So if I know, say, for example, what F does to this sphere right here, and I know what it does in for cells for some already known space, I know the values of my variance, then I can compute the values of my invariance by attaching the cell. Okay? And this will work. Yeah, so this is the source of a bunch of inductive arguments. So anytime I have such a F, homotopy invariants of pushouts become, in some sense, computable. What other properties would F satisfy if this was the case? So if this was the case, I can take, for example, this pushout square. Suppose A and B are pointed, and I wedge them together. Well, if I push out their wedge, then I get 1. Okay, so this gives nothing. So now this is a push-out square. So I apply F to it. Here, F is here. And F preserves 1, and this becomes a pullback square. So I learned that anytime I have such a functor, its value on a wedge is the product of its values. And again, this is another situation where if I look at the homotopy groups here, the homotopy groups are compatible with limits. They'll just be the product. Okay. So more generally, any such F determines a homology theory. Okay. How do we do this? So what's a homology theory supposed to be? Luckily, Peter sort of gave us a definition. So a homology theory is supposed to be some kind of functor. So let me call it F. I'm just going to call it F. Okay. I'm going to abuse notation and call and I'm going to explain why in just a second. So I'm supposed to get a functor to abelian groups. What is my functor given X? I'm going to send it to just pi n of f of x. Okay, so this gives me oh well, okay. I guess in this case it's positively weighted and it's 0 down below some certain f. So I look at the homotopy groups of the output of this functor, and this gives me a homology theory. Why? Well, so first of all, what were the axioms? Peter's going to have to remind me actually, because once you see this, you stop using the Eilenberg-MacLean axioms. So the axioms were that it's supposed to be homotopy invariant, right? But we're working in a homotopy invariant world. So if I have a functor, it preserves all homotopy. I'm working sort of internally to type theory. So we don't have to worry about that one. The other one was that if I had an open inclusion, so a cofibration sequence down to the quotient, that this gave rise to a long exact sequence. Okay, but the cofibration sequence just means that this square is a homotopy pushout. So that just means that I can replace this with a homotopy pushout. And then I apply F to it. But this is what we've been doing. This is the game we've been playing. So when I apply f to this cofibration sequence, it turns it into a fibration sequence. So that means that my homology theory, that my theory thus defined, satisfies the excision axiom, okay, which is the motivation for the name one excisive. And finally, there's one more axiom that you're supposed to have, which is you're supposed to have the suspension axiom, right? So if I take the value of my homology theory on x, and I look at its value on the suspension of x, this is just supposed to be a shift. I'm just supposed to get one more. Okay. So yeah, is this a question, or are you just holding your hand like that? Okay. Good.
It seems so. The linear functor seems to satisfy a slightly stronger property than just this long exact sequence for the excision, right? It could be any fibration or any
push-up. Yeah. So usually when people state excision, they state it in terms of the cofibration, a nice or a neighborhood deformation retract, and that just guarantees that this ordinary quotient square is a homotopy push-up.
Right, but maybe I'm going too fast. But I think your point is going to be that linear functors are homology theories.
We're getting really close, yeah.
But it seems to satisfy a slightly stronger property.
It does, but homology theory is slightly more than this, right? It's also the suspension axiom, which is what I was about to prove. Okay. So we also need the suspension axiom. Okay. And how does this one work? This is again, and we also need the wedge axiom, by the way, but that was what this one was supposed to be. So, well, okay. Okay, so well, we'll come back to the technical. So there's one technical assumption that I'll get to in just a second. But anyway, let's do this one. So how does this one work? Well, I take x and I map it to 1 like this, and I learn that I get the suspension of x here. This is a homotopy push-out square, and I apply f to it. And if f preserves 1, then this becomes f of the suspension of x. But this square is now a pullback. So the pullback here is loose. So this means that if I have this, then I have f of x. I always have the equation f of x is loose on f of the suspension of x. But now I just apply pi n to both sides, and I get pi n here, and this loop bumps this up to pi n plus 1 f of sigma x, which is what we want to prove. Okay. So does that help? And so one other thing that I did not quite say, which will is that in order for this to be computable, we'd also like f to preserve directed colimits. Okay, because if it preserves directed colimits, that means its values on all spaces are determined by what it does on finite spaces. So that's also a technical assumption that you need to add. And I think if you add that, then you'll find that this wedge axiom, I can always take a wedge of an infinite number, but it'll preserve directed colimits, so the wedge will go to the weak product. So you get that as well. Okay. So does that answer your question?
No, but
no.
So is this, if you drop this axiom of the directed colimit, is it topological, or
I think you'll get something slightly more general than the theorem I'm about to announce, which I'm not going to prove. It's a very classical thing, but I think you do need the directed colimits in order to make this true.
But Goodwillie calculus is still a thing that is a legitimate thing, or you should never try to do it. It's like, do you both compute stuff without this directed colimit?
Not that I know of. Not that I know of. I mean, in particular examples, you're always working with functors that you know that satisfy this. So I don't know of examples of people trying to go outside that, but probably something like that can be done.
Sorry, just to say, the wedge axiom also just follows from the push-out. It's again just a push-out.
But it's a finite one. Okay. So if I want the infinite one, then I need yeah.
Is that something you're asking for in the type theory, that it's directed colimits?
Yeah. So I'm giving this classical story in topology, and then I'm gonna do something different when we go to type theory. So right now I'm just trying to give the intuitions, how people set this up originally, and why they're interested in it, and then we'll do something else in type theory. Okay. So maybe I've convinced you. It's not 100% true, but I can look at the each time here I use the fact that f preserves the base point. So that was what I call a linear functor. And I hope I've more or less convinced you, this is not a formal thing, that this is the same thing as what people call a reduced homology theory. And so we've sort of produced this direction. I've sort of extracted it from just the notion of a linear functor. The reverse direction is what people call, well, okay, I'll call it Brown representability, but that's actually okay. I'm going to put a third thing right here, and then I'll show you what. So the third thing I'm going to put here is a spectrum. And so what do I mean by a spectrum? And then I'm going to claim that all these three things are the same. Right. So if you remember, a spectrum is just a sequence of spaces together with equivalences where En is the loops on En plus 1. Okay, this is a standard definition in stable homotopy theory. And actually, this equation right here tells us that we can extract from any linear functor a spectrum, because I'm going to just going to look at the value of f on Sn, right? And my equation tells me that f of Sn, this is going to be my spectrum object in level n, is loops on f of the suspension of things, but that's just Sn plus 1. So I get exactly this equation that I get a sequence of spaces, each of which is equipped with an equivalence to the loop space on the next. Okay, so this is what people call a spectrum. And there's a very classical theorem in topology, which says that anytime I have a reduced homology theory, that it arises, I can construct such a sequence of space, such that my homology theory is given by the homotopy groups of mapping into the space. Well, smashing with the space, but that's okay. So this goes by the name Brown representability. And on the other hand, we've just produced from a linear functor a spectrum. And actually, given a spectrum, you can always produce a linear functor by the following formula. Well, let me not say what the formula is, but I'm just going to sort of take this as a black box. This is a very well-known fact in topology. All these three things are the same. Okay. So the original goal was to have homotopy invariants of X and to compute them by applying some kind of approximation functor to X. And very good approximation functors are like this. They're linear because they convert homotopical invariants into cohomological invariants. Okay, cohomological invariants being those that are compatible with the pushouts in this way. Okay. What am I doing for an eraser here? Do I have to use the thing?
There's one here, and then go to the screen.
Ah, okay. Okay. So yeah, this is a definition that homotopy theorists like, because you replace a lot of these axioms with just this one single axiom about. Yeah.
I have a sort of stupid question.
Mm-hmm.
Why does the variance work out? So this is a covariant functor.
Yes.
But you would expect homology to be covariant.
These are homology theories.
Oh, okay.
These are homology theories.
Okay.
You can the associated cohomology theory is obtained by extracting the spectrum and homing into it. So yeah. But linear functors give homology theories. Okay. What else did I want to say? Okay. Okay. Is it okay? No? Okay. Okay, so observation. Any functor can be forced to be linear. Okay, so if you give me any f, again, probably we're only ever talking about direct equivalent preserving such f. Okay, it can always be linearized. the formula is quite simple. Well, yeah, you'd like f. I'll do this particular case. So you have x here. You have your x, and it turns out for various reasons that these particular suspension squares that we did before turn out to play a sort of crucial role and be the most important. So let's look at something like this. Now, if you give me f and I propose this square to my functor f and I apply f, then it may not at all be the case that this thing is a pullback. Yeah. But I can take its pullback, f sigma x, and I have this. Oops, this way, and I get this canonical map right here. Okay. So I always get this map from any f. I get. I'll write it like this. This map always exists. It's just it may not be an equivalence in general. But this gives the idea to how to fix this. I mean, because just do it again. Sigma x like this, and you can continue the sequence. And in general, this is what people will call P1 of f. And so let me just, as a functor, P1 f of x is the colimit, as n goes to infinity, of loop n f sigma n x. Okay, so I don't have this condition to begin with, but I force this condition. Okay, and I'll give you the classical argument in topology why this works. Why this works is because if I just, I need, okay, no, I can't give you a completely rigorous argument for the moment, but I'm gonna state a much more general theorem later on, but this always gives you a linear functor. Okay. Yeah, this is not trivial to see, actually, not completely trivial, but anyway, okay. To any functor, I can extract its linear part in this sense. I can turn it into a linear functor by forcing this condition. It suffices to sort of do it on spheres or on dimensions. Okay, what else did I want to see? Oh, yeah, so one thing that's not...
this one to your approximator, you're already assuming it's reduced in order to produce the linear one in this process?
Yes, if it's not reduced, I need to do something slightly different, but that's right, yeah. In the reduced case, the formula simplifies. I'm going to sort of describe the general technique later on, so that won't be a problem. Right, otherwise, actually the formula is the same, but I need to take loops over f of 1. So it's still the pullback, but it's just the loops needs to be thought of as 5-wise for f of 1. But anyway, okay. So one remark is that, and what's slightly suspicious the first time you see this, is as was sort of pointed out, well, the identity functor, or the forgetful functor, if you like, forgetting the base points, is not linear. Because it takes colimits to colimits, not colimits to limits. Okay, so this is a strange feature of this calculus, that the identity is not linear. So what happens when you apply this procedure and linearize the identity? Well, so if I take P1 of the identity, this becomes just the colimit as n goes and evaluated x. This is the colimit as n goes to infinity of just loop n sigma n of x. This is a very famous construction in homotopy theory. It's the stable homotopy type of x. Okay? So the homotopy groups of this object are the stable homotopy groups of my original object, essentially by definition. Yeah, by definition. But of course, there's a little bit more to say than that, but that's true. So in other words, this is why people say that stable homotopy is linearized, or the linear approximation to ordinary homotopy. Because it's what I get when I linearize the most naive approximation of my space, which is itself.
It's like, that's why you're calling this linear.
Yeah, okay. Yes. This is a long, yeah. It's a little bit curious, but I don't know. Okay. Yeah, that's another reason. These spectra, they're like abelian groups. They always have an addition on them, and we're going to see that actually later. Why linear things have an addition. So that's an important part of the story. Yeah.
Also, the homotopy category of any stable infinity category is enrichment of groups.
So yeah. Yeah, so linear in the sense of linear algebra. This turns a non-linear object like a space into something which is linear, and we'll see next time this sort of addition. Okay. So, great. Well, so we've seen that this linearity condition, this switching colimits into limits, is essentially all about push-out squares, right? And it's essentially, well, as you say, it's a little bit more. It's the axiom of excision for your homology. Okay. So you might wonder, and Goodwillie was probably the first one to wonder this. Does there exist a more general notion of excision? Okay, can I think of excision? Can I generalize this condition and think of higher versions of excision, which are not exactly like this? And you can do this. Okay, what does it look like? Well, we're just going to pass from squares to cubes. Okay, so we're going to look at the following situations. Suppose that I have a diagram that looks like this. EF, I guess this is G, H. Let's suppose that I had a cube like this, and let's suppose that every face is a push out. Okay, so I have a bunch of things that should be excessive somehow that I'd like to be excessive, and so I'm going to say F is too excessive. And the definition might be a little bit surprising, and there's well, but it's the right thing. It's what works. If for every strongly co-Cartesian, I'm using actually I can just do it right away with n because nothing's going to change, and I'll explain. I'll illustrate with two. N plus 1 cube. F, let me call this cube x, and I'll imagine evaluating, well, let me call it script x, and I'll imagine applying f to each of the elements of the cube as f of x is Cartesian. And so what do I mean by that? So strongly co-Cartesian means the input cube has every two-dimensional face a push out. Okay, so I don't just want the whole cube to be a colimit diagram. I want all of the faces individually to be a push out. Yeah?
But the condition that the whole cube is a colimit is in addition to that.
It follows. I mean, yeah, it follows. If all of the faces are push outs, then H is the colimit of the whole cube, but it's stronger than that.
Okay. And there's a thing to use.
Yeah, everything can be used. So that's what strongly means. Strongly. Is that it's not just co-Cartesian, also all of the faces are, all of the two-dimensional faces are push-out squares.
Is there any two?
Sorry?
Is there a good reason for
yes. No, slightly more than that. We'll come back to it. I think I'll give you a reason later on. There's a number of reasons, but it's difficult to see when you first see the definition. I admit that. So anyway, so you apply F. Yeah, I guess I am going to look out. How fast can I draw a cube? I mean, you get good at drawing cubes in this subject, so maybe I can do it. I should have done that. You're right. Okay. Okay. And the output cube after applying F, I just demand that it's Cartesian, meaning the initial object is the limit of the rest of the cube. Okay, so that's a slightly weaker condition. Okay, but that's the definition.
know if I pull back to do this long XX sequence.
Mhm.
But if I have,
That's right.
what happens?
It's more complicated.
Do you get spectra?
We'll get to that. Yes. Exactly. How much time do I have, by the way?
25 minutes.
Okay.
Because it's followed that f is n excessive, then it's also n minus 1 excessive.
And plus one excessive. Yes. This. So a linear thing is also quadratic, but in a trivial way. Exactly. Okay. Yeah, I'm not going to prove all these statements today because it would be a bunch of work, and I just want to give you. I'm going to prove them differently. The next slide. What's that? Oh, here there's something to prove. Yeah, but I guess it should be pretty easy. I mean, yeah, yeah, it's easy because yeah. There's various ways to see it. But. Sorry. Yeah. Right. Yeah. So if I exactly, so I can apply f in each side, and they will both be Cartesian, and then the fiber of the map, then it will have to be trivial because they're both Cartesian, and so I'll get a map of cubes, which is level-wise sort of. There's various ways to see it, but okay. Yeah. Okay. Right. So. Yes. So more generally, so every f. Yeah. Every f admits an excessive approximation. Okay. And let me just describe for you the construction with the cube, and it's going to be very much analogous to the construction we did previously, which is it turns out I take my f. It turns out to be sufficient to think about particular strongly co-Cartesian cubes, which are these trivial ones. Okay, trivial, canonical. I don't know what you want to call them. So what happens when I iterative? So I'm going to form the co-Cartesian cube generated by this by just iteratively taking a push out. So here I get suspension x. Suspension x. Okay. If I push out the back face, I get suspension x. And if I push out this face, I get suspension x. What am I doing? Like this. My cube goes. Okay. And the only maybe mystery is what I get right here. So I'll draw a picture of it as opposed to, maybe if suspension x looks like this, then this thing here looks like this. Okay, it's got it's x with not 2 cones glued to it, but 3 clones glued to it. Okay, I'll let you figure it out. Exactly. So in general, you have this cube. If you give a space x, you have this cube. Let me define it x sub n, which is defined on the partially ordered set of subsets of n as a set, maybe n plus 1. Well, I'll just define it this way, the spaces. And I shouldn't call it f. Let me call it, I don't quite want to call it t. Let me call it like sort of tau. Okay. So you fix an x, and what is tau n of x at a particular k, which is a subset of n, it's just x join k. So here we have the subsets of the 3-element set, and when I join with a set, when I join x with a subset consisting of a single element, I'll get a point. It'll be a cone. It'll be contractible. When I join x with the subsets of 3 consisting of 2 elements, I'll get a suspension. And when I join x with the subset consisting of 3 elements, I'll get this funny-looking triple hat. Okay. And so in general, so I can define, given f, I can define a new functor, which is t, which I'm going to call Tn of f. And what does Tn of f at a space x is going to be the homotopy limit. Oh, wow. I really am doing formal topology because I just said homotopy limit. Anyway, over the k, which are non-empty, in P of n, of subsets of n, of this tau n of x. So what is my construction? It's exactly what I did before in the case for n equals 2, where I had this picture right here. I took the suspension of x. I applied f and I took the limit by forgetting this initial object. And because of that, it has a canonical map from x to this limit. And the same thing here. I apply f to this crazy looking thing that I generated from x, and I'll have a map from f of x to the limit of this thing. Oh, yeah. So I apply f. Okay. So this gives me a natural transformation like this. And so I get this sequence, f, mapping to, this time I'm not going to write the argument, to tnf, to tn squared f, I do it again, to tn cubed f. And I take the colimit, and this is what Goodwillie calls Pn of f. Okay, and so theorem, and this is not trivial. Pnf is always an existence.
What is under the limit?
Yeah, so f.
I mean, under the k difference.
Yeah. So the subsets of n. So let me write this: k contained in n. The underscript means the finite set. So a subset of n, which is non-empty.
Okay.
So that means that I don't take the. Otherwise, I'd have this initial object. Okay. And then it's f of this thing I call tau n of x. Okay.
And all the PNs are idempotent, right?
Yes. Yeah. So that's because if x or if f is n excessive, then this is a strongly Cartesian cube because it's obtained by pushouts. So by the definition of being n excessive, when I apply f to it, I get a pullback square. But that just says that if Pn is n excessive, that this map is an isomorphism and continuously. Okay, so it's clearly idempotent. That's not the hard part. The hard part is to show that it's n excessive. Okay. Okay. So I keep losing the eraser. I guess this is a problem. Okay. Okay. Second observation.
So in the whole limit, there has to be a k on the right, no?
Yes. Okay. So if I write, okay, so I defined this Tn, but I can just say it directly. I mean, I'll just write it like this. I apply f to my cube. This is the definition of my cube, but I guess I don't really need it. Yeah. Okay. What else do I want to say about this? Okay. Why? Right. I just want to give an idea. Why do people sort of care about this thing, right? Okay, so because in a particular nice example is that I can look at Pn, as we saw, the identity functor is highly non-linear. It's also non-n excessive for any n. This bizarre condition requiring that some sort of colimit cubes get sent to limit cubes is just not satisfied by the identity functor. So that means that you have this map. So instead of, I'm just going to draw this tower. I take x, and I map it to P1 of the identity of x. I mean, everything that I'm going to write in this tower is just completely canonical. And this we said was the stable homotopy type of x. Yeah. So all of these things map to each other. Yeah, right. So I can now look at P2 of the identity, and I apply it to x. And it turns out that P2 is not linear, but it will always have a map. You can think of this as analogous to a kind of Postnikov, generalized Postnikov tower of the identity functor. Okay? But we're going to see something special about it. So then I can take P3 of the identity and apply it to x. And I mean, x will map to all of these things. And so the result is, here is where you get your spectral sequence that you were asking about, right? So this says, well, if I suppose that in good cases, for example, if x is, I think, connected, maybe simply connected, this tower will actually reconverge to x. I'll get x back by taking the limit of this tower. And anytime I have a filtration like this, I get a spectral sequence. So the result is that I'll have a spectral sequence which starts with the stable homotopy groups of x and computes the unstable homotopy groups of x. And it's filtered by the successively more complicated and excessive approximations of the identity functor. Okay? So this is why I think I said in my abstract that Goodwillie calculus is a way of interpolating between stable information, which we can think of as like linear, the first order approximation, and the infinite approximation, which is x itself in good cases. Okay? So that's why homotopy theorists are interested in these towers. When I put x equals a sphere, these are the most sophisticated ways we have of computing unstable homotopy groups of spheres arise from these sequences, because they're, in some sense, yeah, maybe because they're so unbelievably canonical, starting with x. Yeah, anyway, yeah.
So is this theoretical tool, or can it actually be used to compute?
Oh, no. It's very much used to compute. I think people who, yeah, there are very nice theorems about what happens when you take x to be an odd sphere and you localize with respect to homology. So there's lots of things, more things you can do to simplify, but there's very sophisticated unstable calculations that are made really with this. I mean,
is there a dual version? Now you have x mapping to this tower.
I don't think there's a dual version in spaces. There are other dual versions. So you can take this idea about converting colimit cubes into limit cubes, and you can start to just you can just repeat everything starting with any two categories and start to play a lot of games. So there are many variations on this basic idea, but I think the theme is always the same, which is that if you convert colimit constructions into limit constructions, homotopy becomes easier to compute. I think that theme is kind of universal in this subject. Okay. So that's that. So this is why I think homotopy theorists are very much interested in these things. They create very structured, very rigid ways of approximating unstable homotopy theory by stable homotopy theory. Of course, this problem is, hugely unsolvable, but in the range where you know it, you can make some progress. And let me just say one more thing. So probably, yeah. So S1. S0. Let's. Okay. Yeah. S2. S3. 1, 2, 3. I'm not really going to fill these in. It would be impressive if I knew all the groups. I mean, lots of people do, but I don't. Yeah, you have this. Here's our table of the homotopy groups of spheres. I got one stable stem, right? Okay. 0, 0. Oh, that's not 0. Oh no. I don't know. Okay, 0. Okay. And probably we all know. So you have this nice diagonal here. You get Z, and but you have a little bit more because these every time you have the by the Freud-Bell suspension theorem. So let me just write it. If I have a space X, I mean we've been considering this thing quite a lot, where I take the suspension of X and I look at the loops of X. And then loops of the suspension of X. And the Blaker's-Massey theorem tells you that if this is n connected, and this is n connected, that this map here is 2n connected. And what that says in terms of the table is that there's a range, there's a line here of slope, -1/2, something like this, -1/2, where if I look at, if S3, for example, is this connected, then for a range double the connectivity of this thing, these groups will stabilize along the diagonal. Okay, so this gives me, yeah, so let me try and draw it again, something like this. And you have this range here where if you go along the diagonal, the n equals 1 diagonal, the groups don't change anymore. And this is called the stable range. And this is the range in which if I want to compute the unstable homotopy groups of S3, I can just replace it with loop infinity sigma infinity of S3, because all of those maps in the tower, S3 mapping to loop sigma S3, mapping to loop squared sigma squared S3, all the way down to the colimit, loop infinity sigma infinity of S3. All of these maps are 2n connected. So if I stay in the homotopy groups which go out to twice the number of zeros right here, I can replace these homotopy groups with these homotopy groups, and I'll get the same answer. Okay. Now, so one of the things, here's one of the reasons these cubes are what they are. So there's a cubical version of the Blaker's-Massey theorem. Okay. So if I take a push-up, so I get to draw a cube again. Oh, you got to remember not to erase the cubes. I think that's the key thing in this. So you take your cube, F, this is like this, G, H, okay, here's my cube. Okay, and if this is K0 connected, and this map, I'm looking at the initial maps from the initial objects, that's K0 connected, that's K1 connected, and that's K2 connected. And the square is strongly co-Cartesian, so all of the faces are push-out squares. And I take its homotopy limit, so I take the limit of the rest. So the map from A to the holim of this thing is holim cube X is the sum connected. Okay, so K0 plus K1 plus K2. So you have this nice generalization. Okay, so if I apply that to this cube over here, I take the pullback of this kind of crazy looking thing. I get this new space. It's by our definitions, it's exactly T2 of the identity of X. Okay, so it's X mapping to T2 of the identity of X, which before T1 would have been this loop suspension thing that we did over there. This map, if X is n connected, is 3n connected. Okay, not 2n connected anymore. It's 3n connected. And similarly for the rest. Okay, so this means I can continue off, and I get here P2 of the identity of X, which is the colimit of this sequence. And all of these maps are 3n connected. So that means if I go back over here to my table, I can draw a line of slope -1/3. Okay? And if I want to compute any of the groups in this range, this is called the metastable range, then I can replace the sphere with P2 of the identity of the sphere. Okay? And this is the start of an infinite sequence of lines that go like this, which are the lines that I'm seeing in this tower. Okay? So in a range, depending on the connectivity of X, I can compute the homotopy groups of X by computing the homotopy groups of its nth order approximation. Okay? So this is another reason why, so I just wanted to draw this picture and explain. I think a lot of us have heard of this range. Now, be careful, because what's nice in the first approximation is that I do, over here, did I take it off the board? I do X mapping to loop sigma X. And if X is a sphere, I still see homotopy groups of spheres. So that means that when I'm in this range, if I look at a homotopy group, I can see what its value will be one step down, because it's also a homotopy group of the sphere. Whereas in the more general case, it's a homotopy group of something slightly more complicated. So you won't see it in the table in the same way. But nonetheless, these groups are can be calculated by replacing them with a kind of approximation.
But stupid question. Shouldn't the lines be going the other way? Like more towards the unstable range?
Well, this is the unstable, right? So the stable range is twice the number of zeros. And so the metastable range will be 3 times the number of zeros. So, so I think
metastable is a sub range of the stable.
no, it's more. These are where the groups are non-trivial, and these are also where they're non-trivial, but they don't stabilize. No,
I thought that everything to the right of the line stable.
no, to the left, between the line and the diagonal.
Oh,
So this is slope -1, and the stable range is between -1 and -2, and the metastable range is between -1/2 and -1/3.
So it means he stabilized. It means that if you go down on this diagonal, they're all the same.
No, that's what I was just trying to say. So that's true here because of the accident that our approximation, when I have a sphere, gives me back a new homotopy group of a different sphere. Whereas here, it gives me back a homotopy group of something else. So it won't just be in the table. I won't see the same simple, this stabilizes. It's just that I can replace it with something which is morally easier to compute.
First thing it is, but for the stable thing,
Yes.
it is.
Yes.
and every diagonal eventually goes in the stable.
Yes, exactly. And every diagonal will eventually hit that. Yes, that's right. Yeah. Okay. What's happening? 4 minutes. Okay. So okay. So I'll just sketch what happened, and then I'll pick this up next time and do it. Okay. So this is why homotopy groups are homotopy theorists are interested in this. It gives a systematic way of approximating unstable information. But what have we done? Okay. Well, we started with, I said that we were thinking about functors from pointed spaces to spaces. But I said that they should preserve directed colimits. So that means I can just replace this with finite spaces. Okay? So, I mean, a functor which preserves colimits is the same thing as its left conextension along the restriction of finite spaces. Okay? So that means we're considering objects f in the functor category from finite pointed spaces to spaces. Okay? And this is a topos. This is the topos, which I'm going to write it like this. This is the topos which classifies a pointed object, okay, higher categorically. And what did we say about this? Well, we said that for every n, there was a functor, Pn, which reflects f into an n-excessive functor. Okay? And this thing I calculated, I showed you how to construct it. You take f and you map it to this thing Tn of f, and you map it to Tn squared of f, and then you take this colimit and you get the colimit as n goes to infinity, Tn k goes to infinity of f, and this is the definition of Pn of f. And the theorem is that this is a localization. It really proves the localization. But so this Tn here was only defined using a finite homotopy limit. Okay, it's the homotopy limit of a finite dimensional cube. And on the other hand, this is a colimit, a directed colimit. So the definition of Pn is in terms of finite homotopy limits and finite colimits. And that means that actually, what? And filter colimits, what did I say? Yeah. So that means that Pn itself is left exact viewed in this functor category. So if you imagine taking a limit of f's, some finite limit of f's, and you perform this construction, I have a limit in this direction and a directed colimit in this direction. I can change the two. So that says that Pn is left exact. So what we've done is we've produced an infinite tower of left exact modalities in this topos classifying functor. And so now I hope we see the connection with type theory. So this is just a, yeah. So I'll stop here and we'll pick it up next time and talk more about these modalities. The same thing from that point of view.
F.
Yeah.
I know it's just a metaphor, but I think of it as a kind of derivative, and I kind of think of the whole sequence as kind of Taylor.
Exactly. That's the original intuition of Goodwillie, is that these two things, that Pn, but Pn is the nth polynomial approximation to my functor F. And this, with this slightly strange notion of polynomial.
But in a very figurative way.
There are lots of things that you can do that make it a little bit more than just an analogy, but it's true that it's somewhat strange when you first see it. Yeah.
This is, you can take the homogeneous part, which you bring a fiber of Pn,
Right.
Pn minus 1, the homogeneous part. And there's a formula that is like a Taylor formula.
Right. That's exactly right. So if you have a functor Pn minus 1 of f, and it maps to Pn of f, and suppose everything was pointed. So suppose you had a base point here. You can look at the fiber, and Goodwillie calls this Dn of f. And it has the property that it's homogeneous, which is to say that it's n-excessive, but it also, all of its lower, just like the Postnikov system, all of its lower PNs will be trivial. And so Goodwillie calls this a homogeneous functor. And there's a theorem that the homogeneous functors, if I have, let me call it D, which is n-homogeneous, then it's necessarily given by the following. X, then there exists a spectrum, E, together with an action of sigma n, such that this functor is given by smashing X to the n times, together with taking the quotient over the sigma n action. So the fibers of these things are monomials where the numbers are spectra. Yeah.
So this is like the sigma is the dividing out.
Yeah, and this is over n factorial, if you like. Exactly. So the analogy can be pushed pretty far, even though it starts out pretty strange. There's a notion of what it means to be analytic.
And then also, if you look at, isn't there some theorem saying that the Pn plus 1 is, or something, is determined by this part, just like
right. So there are lots of theorems that say things along the lines of, if you have a map between two functors and it induces an isomorphism on all the derivatives and some maybe analyticity condition, then it's actually an isomorphism on all, say, connected spaces for some k. So there are lots of things along this line. You have things like, if all the derivatives vanish, then it's locally constant. And so you can do there's lots of stuff you can do.
I was thinking though, isn't there a way to use this this fullbacks where you've just drawn to actually build general functors?
Yes. So
by attaching new things.
Yeah. So just like the Postnikov tower has, if you think of this as kind of a Postnikov tower, when I look at the fiber, it's always an Eilenberg plane space. So it's always classified by a map to the space of Eilenberg plane spaces. And so there's a space of n-homogeneous functors, and every extension is classified by such a map. So yeah.
So when defining an existence, that can commute in n cubes.
Yes.
Do you know how to define that internally?
Well, so there's two answers to your question. One is that I think yes, but that's not what I'm going to do next time. I'm going to show a different way to sort of describe this tower without using. I'm not going to give these definitions in HoTT. I'm going to change the story so that the internal language here replicates these definitions. But yeah, so. Yeah.
Sorry, what is S adjoin X point?
It's the topos classifying a pointed object. So for every topos E, an algebraic morphism from this topos to E is the same thing as an object of E together with base point.
So what are the pointed objects corresponding to PNs inside that?
They are, well, the identity functor lives in here. And so you apply Pn to X itself, and that's the universal example, right? So what, sorry, what was your question? Yeah.
Yeah, I mean there must be a pointed object in this functor category, in this topos itself.
Yes. So there's a kind of universal n-excessive object which is obtained by applying Pn to the universal object itself. And I'll try to describe next time what that classifies.
And it's the inclusion, right, of the finite spaces into space.
Yes, that's X. X is the forgetful map, yeah.
So what is the local functor?
I forget, so yeah.
Okay.
I don't know on top of my head.
First of all, very nice talk. And I wanted to ask if you want to apply this to, so the functor, this Goodwillie calculus can kind of see how space is built out of spheres in some sense, just like
yeah.
that's how it's kind of determined. But what if I want to apply this to kind of a geometric setting or maybe like motivic setting where you might have different ways to build up spaces?
Yeah, that would be great.
Wait, doesn't a lot of this stuff apply? Like at least that. So I'm still waiting for your paper to come out, but doesn't a lot of this stuff apply when you don't talk about spacing? You can say C and D are just category satisfying axioms, and probably motivic spaces might.
I don't think that's exactly what he's looking for.
So the thing is that, yeah, so motivic space is not a topos, but you take a topos. I don't know.
No, you don't need a topos.
Yeah, you don't need a topos. But that thing will have spheres, but not all objects are built out of spheres in this topos or whatever.
So it is true that you can develop it in that much generality, but I think what he's looking for is there some category for who the linear approximation is motivic spectra, which is a slightly different question, right? So you can, of course, just take the motivic category and whatever functor you like between it and approximate it, but there's no a priori reason that you'll get motivic spectra or something like this. You probably have to find a setup which gives you that, which may not be the naive thing to do, right? So I think that was more your question, yeah, something like this. And that I don't know.
Okay, so I think we're all still full of questions, but let's pass to the unofficial part. Release Eric from the
Thanks for the message about
I found that Michael Chang thing.